Okay, all right, so today we're going to be building off of what we did last class period where we were learning about structures, and really last class period was about reviewing what you did in Chem 1A regarding chemical structures, Lewis structures, and interpreting those Lewis structures to get hybridization information, geometry information. So one of the examples that we did is we showed this molecular formula right here, and we showed that there were actually two different Lewis structures that we could draw from that molecular formula, okay? So to be clear, this C2H6O, this is what we call our molecular formula. How many carbons, how many hydrogens, how many oxygens. You can figure out the molar mass of a compound from your molecular formula, and you use molecular formulas a lot in general chemistry. For ionic compounds, that's all you need is a molecular formula, right? That tells you all you need to know for that compound. But in organic chemistry, this is quite simply not enough information. Okay? So that's why we have to use the structures of these molecules. But drawing out a Lewis structure takes a lot of time. It's kind of a pain in the butt, not to mention that things get quite busy when you get larger molecules. All right, so we have these shorthands that we use in organic chemistry, and that's what we're going to go over today, what are called condensed structures and bond line structures. All right, so the first one we're going to do is condensed structures. I'm going to put some examples down just so we can kind of see what it is, and then we'll go over some rules about how we do our condensed structures. All right, so for this first one here, our condensed structure would be CH3, CH2, OH. All right, that matches our first structure above, and let's see if we can make sense as to how it matches. Well, this first unit in my molecule is a carbon with 3 hydrogens. So we list CH3. We move on down the line. We have this one, a carbon with 2 hydrogens, CH2. And then the next one is that alcohol group, that OH group. So that's that last component of our condensed structure. All right. If we want to be good, we can put lone pairs on the oxygen in our condensed structure, but typically you won't see them on there, and I'll talk about why that is here in a second. All right, let's move on to the next one, because again, our condensed structure should uniquely point to a molecule. So we're not going to be able to use this same condensed structure to match both molecules. So for this one over here, our condensed structure would be CH3. Now we have the O next in line, followed by that last unit, another CH3. Okay, and again, just to sort of see how these match up here, we have a carbon with 3 hydrogens bound. That's our first CH3. Now we have that oxygen in the middle. That's our O. And then lastly, on the other side, another carbon with 3 hydrogens, or a CH3. All right, so we would use a different condensed structure to represent these two different molecules here. So again, representing that same information, that same structure, but in this little bit of a shorthand that we have here. Okay, so we're going to do a ton more examples here, but right now I'm going to skip and I'm going to leave. I'm going to start like laying down some rules. We want to leave like a good amount of space here on our page, because we're going to kind of hit these like one by one here. Okay, so first of all, your condensed structure. This is a way to represent a molecular structure using a single line of text. Okay, and so these things are most important for computers and textbooks and databases, things where we need to convey the structure of a molecule, but all we can do is type it out in one line, right? You can't draw a Lewis structure in your computer without some sort of a fancy program. But using just a Word document, you can do the condensed structure of that molecule. All right, so like I said, we don't put our lone pairs on our condensed structures, or we could if we wanted to, but generally speaking, when you encounter these, you won't see lone pairs on there, and that's because you don't have an O with a lone pair button on your keyboard, right? So again, this is something that's really popular when we see it encountered in a textbook, or if we want to search a database or something like that. All right, so because of that, my main concern with your ability to interact with these condensed structures is to be able to read these condensed structures. We'll get a little practice writing them out as well, but generally speaking, when we do our molecules on our notebooks and in our exams and everything like that, we're going to be drawing out those structures, right? So my main concern is that when you read one of these in the textbook or something like that, that you encounter any sort of a condensed structure, that you know what it's saying, that you know how to read these. So that's what we're going to focus on here, is reading these condensed structures. All right? Cool. Let's do another example and see if we can't, figure it out based on what we've done just by analogy thus far. We are going to lay down our first rule for these condensed structures. And this is the most important rule of all of them. That's why it's rule 1. And that is, your structures still must obey that octet rule. Remember those bonding patterns that we laid out on the first day of class? You have to keep those in mind when you're translating these condensed structures. All right, make sure you don't put down a carbon with 5 bonds or a carbon with only 2 bonds or something like that, right? You're still obeying those rules that we laid out at the beginning. Okay, so what I'm going to do is, again, I'm going to leave some room here for some extra notes, and I'm going to go to the next page here to do an example. And here I'm going to give you the condensed structure, and I want you to tell me what the Lewis structure is for this molecule. Okay? The other thing that you're going to see that I'm going to do with these examples is I'm going to leave some space over here for the next type of structure that we're going to talk about, these bond line structures, so that we have all 3 representations all in one place and we can kind of compare and contrast. All right, so just a way to think about spacing out your notes. For right now, you're going to give me the Lewis structure of this molecule, again, based on that condensed structure that I'm giving you. Okay, so we have that first carbon with 3 hydrogens on there. Okay, we have another one, but this one's in the middle, so it only has 2 hydrogens on there. Another carbon with 2 hydrogens. And then lastly, when we get to the other end, again, we need that carbon with the 3 hydrogens. Okay? One thing I want to point out, and you'll notice this with all of our condensed structures here, if you see CH3, where must that be in the molecule? Well, it's got to be located on one of the endpoints there, right? The only way you can have a carbon with 3 hydrogens bound is if it's on one of the terminal ends of our molecule, right? So this must be on the end. We see these CH2s. These are the ones that are going to be in the middle. All right. I'm going to show you another condensed formula that we could use for this structure that's even more condensed than this one, all right? So this one's perfectly acceptable, but we could even shorten this even more by writing CH3, and then in parentheses, we're going to say CH2, and then put a 2 on the outside. This is how we indicate that there are 2 repeating units of that CH2. And then I need my other end cap here. All right, so these parentheses with this little subscript on the outside, this indicates here a repeating unit of, in this case, CH2s. Okay, so let's just go back up to our rules and kind of just note that we have this that we're going to see for repeating units. We are going to use parentheses with that subscript. Okay, we'll just put down an example here. That was our CH3 in parentheses CH2. Now, in this case, either one of those condensed formulas were equally as convenient. It's not like I saved myself a lot of writing. Let's say that we had 8 different units of CH2. Then all of a sudden that saves us a lot of writing, right? So whether or not you would use these repeating units sort of condensed formula here really depends on how convenient it is. All right, but anytime we have repeating units, we're allowed to use these parentheses with that subscript to help condense things even more. Cool. All right, so let's do another example now using that notation. All right, again, I'm going to kind of leave some space for both a Lewis structure and a bond line structure. And I want everybody to take a second and draw the molecule corresponding to our condensed formula here. All right, again, you're going to give me the Lewis structure of this molecule, and we'll save this bond line structure here for when we get to it. All right, so everything kind of starts all nice and normal, CH3, CH2, and then we get to C, and then we have 3 repeating units of this CH3. So what maybe we're tempted to do is say, all right, C with 3 H's, another C with 3 H's. What's the problem with what I'm doing here? I'm breaking the octet rule, right? So again, rule number 1 was rule number 1 for a reason. We gotta follow our octet rule. And like I said, we see CH3, we know this has to be at the very end of a molecule here. So this isn't telling me that they're all in a line here. It's simply telling me that I have 3 of these CH3 groups attached to that carbon there. So I don't want to put them all in a line like this. And this is where things get really crowded, and this is why we're not going to use Lewis structures after today. We're going to use these bond line structures instead. But what we're going to do is we're going to have this carbon, and it's attached to 3 different CH3 groups. Okay? This is going to be a lot of how life is going to work in organic chemistry, is a little bit of trial and error. You're going to start trying to do something, and you'll put down a structure. The most important part is being able to take a step back and say, all right, something's wrong here. I need to take a step back and redo things, make sure that my octet rule is satisfied. Trust me, as you get better at this, you'll have no problem reading these condensed structures, but at first there may be a little bit of trial and error, a little bit of rearrangement that has to happen on the page, and that's going to be true with a lot of stuff that we learn. You got to not be afraid to make a mistake and then go back and look at your work and be like, okay, something went wrong here. Let me try something else. Okay? Cool. So here we go. All right, so now what I want y'all to do is everybody's going to take a second. I know it's early in the morning and nobody wants to talk to anybody, but you're going to introduce yourself to your neighbor real quick. It's going to be awkward. Yeah, hi, how are you? Great. Everybody, introduce yourself. Let's go. Talking. Wonderful. Awkwardness. Excellent. Cool. Awesome. All right, so what we're going to do is we're going to work through these examples here, and you're going to use your partner to check your work. I'm going to float around. If you guys have any questions, you can ask me, and then we'll sort of go over these together. But here are 4 condensed structures that you're going to translate into Lewis structures for me. One thing I want to point out before we get going here is I have Cl on this formula here, chlorine. And if we look back on our cheat sheet here for our bonding patterns, we don't see chlorine anywhere. So how am I supposed to know what the bonding pattern of chlorine is?
Up and down on the periodic.
Yeah, everybody in what we call a family on the periodic table, they all have the same bonding patterns, right? So if we go to our periodic table here, chlorine is in the same family as fluorine, bromine, and iodine. All of those will have the same bonding patterns. Right? Likewise, nitrogen and phosphorus have the same bonding patterns. Oxygen and sulfur have the same bonding patterns. Everybody in a family shares those same bonding patterns that we went over. Okay? All right, cool. So here are your 4 examples. Not that. And you're going to go through and you're going to draw these structures. Oh, wait, I lied. There's one more thing we got to do first. Haha. Back up. One more rule we're going to add to our list for condensed structures here. We saw our repeating units. There's one more that we need. Okay? So this last format is for large groups that are off that main chain. We'll say off the middle of the main chain. For that, you use parentheses as well, but without any sort of a subscript. Okay, so what do I mean by that? Okay, let's do an example. Let's say that we saw something like this, CH3, CH, and then in parentheses OH, CH3. These parentheses here, without any sort of a subscript, is telling me that this group of atoms, the OH group, is sticking off of the main chain of that molecule. So if I were to do my Lewis structure, I'd do that first, CH3. I get to my next one. It has this carbon with 1 hydrogen, and then sticking off is this other OH, right? So this group right here, and then I guess just to finish this off to make a point, this group right here is pointed off of that main chain, okay? My Lewis structure isn't quite done yet. What do I need to include? Lone pairs, right? We can leave them off of our condensed structure. Again, you won't see them on your condensed structures because, again, those are for when you're typing them into a computer. When we're drawing these things out, we absolutely have to include our lone pairs in either our Lewis structures, and same thing will go for our bond line structures as well. Okay, cool. So parentheses with a subscript is going to be a repeating unit. Parentheses without a subscript means that it's sticking off of that main chain. A large group sticking off of that main chain. Okay, great. All right, so everybody, we're going to take a few minutes, and you're going to try to tackle these 4 examples here. Oh, and like before, I would leave a little room to do bond line structures for these as well, because we're going to do the Lewis structure right now, and then when we learn how to do it, we'll do the bond line structure as well. So again, we have an example of all 3 structures for each of these here. So if that was the case, you would see some sort of a charge, which isn't there. So you want to try to rearrange things in such a way that you don't have any sort of positive charge or negative charge or anything like that. about anything, snag me while I'm walking by and let's have a conversation about it.
Yeah, so the only thing that we're missing is just the pairs. Yeah. Yeah. It's not gonna work with the No, you're missing a CH in front of it, but then you won't. So in between the CH2 and the parentheses is marked CH.
The first one's here.
So let's do the CH2 next. That one I think we get out. Alright, and then we got CHO, so let's try that. Alright, and what's the problem with your carbon? So I got 3 bonds, so what's wrong with your oxygen? It's only 1. So let's try higher order bonds. Maybe that makes everybody happy. So if it doesn't work with them all in one like this, because your oxygen's not happy right with it. So just don't put them all in one. That's the bond. So So you're close. So let's try this carbon needs that last one. It needs a higher. So let's put hydrogen on there. Doing better, right? And then let's put oxygen on there as well. What's wrong here? Right. So oxygen likes to have how many? 2 bonds, 2 lone pairs. Carbon likes to have how many bonds? So this isn't going to work with a single bond, but let's just try higher order bonds. Yep.
You know how oxygen likes to have the 2 bonds between them? But I could be wrong.
All right, let's do it. Let's go through it together here. Okay. So for this first one here, let me make some room. Everything starts off all nice and normal. We have a carbon with 3 hydrogens, a carbon with 2 hydrogens. Then we get to this CH, and then we have CCl3 in parentheses with no subscript. So what does that mean with they're in parentheses with no subscript? Pointed off the main chain, right? So that means that we have a carbon that has 3 chlorines attached to it, all sticking off of that main chain. Okay, all right, and then after that, we just have another CH3 group. What's wrong with this structure here? What do I need to include? Lone pairs, right? So again, lone pairs aren't represented in our condensed structural formula. We got to put them in because we know by bonding rules, chlorine should have 1 bond and 3 lone pairs. Cool. All right, so now we get to this one. Again, we start off, everything's nice and normal. CH3, CH2. And then we get to this one, which is C with an H and an O. And I'm going to get to this point here. I've written down all my atoms from my formula, but I take a step back and I look at this and something's wrong, right? My carbon's not happy, my oxygen's not happy. I can't just add more atoms on there, but what can I do that's going to satisfy the octet rule for both of these? Double bond, right? So that higher order bond I know is going to satisfy my octet rule. Remember, rule number one's rule number one for a reason. You need to make sure that the structure that you draw at the end of the day has your satisfied octet rule. And I'm going to be good and put in my lone pairs as well. Cool. All right, so then we get to this one. A carbon with 3 hydrogens. Then we get a COCH3. Something's wrong here, right? Who's not happy? Carbon, right? I can't just go throw in a double bond. And that was my strategy last time. This will give carbon a higher order bond, but now my oxygen has 3 bonds, which it doesn't want, right? So if you can't put them all in a line without breaking your octet rule, then maybe this oxygen isn't sitting all in a line like that. Maybe I need to point that off of my main chain, right? So again, always going back to that first rule of making sure that your octet rule is satisfied. And I'm still not quite done here. I need to include a carbon-oxygen double bond in order to satisfy everybody's octet rule. Okay? All right, and then the last one, we're kind of going to get a similar problem. I think everybody's tempted to say, all right, CH2F, CH2. And again, right off the bat, we got a problem here. Right? Who's unhappy? The fluorine, but also my carbon, right? Remember, if it's going to be on the end, it's got to have those other 3 bonds. So what we said last time, and this is a good illustration, are these halogens are a lot like hydrogens. They only ever have 1 bond. So much like hydrogen, they'll always decorate the outside of the molecule. They differ in that they need lone pairs as well, all right? But remember, your halogens are like hydrogen with only 1 bond. So they're always on the outside. So CH2F doesn't mean that the F is the next one in a line. It means that like my hydrogens, that fluorine is on that first carbon. You could have put it on the left, you could have put it on top, you could have put it on bottom, right? The position doesn't matter. The point being is it needs to be connected to that first carbon. Now I have CH2. Now I have an N. Let's remind ourselves, what's nitrogen's bonding pattern? 3 bonds. So 1, 2, 3. And then I need that lone pair. Cool. All right, so here are our 4 examples here. We have our condensed structure, and then we drew that Lewis structure by reading that condensed structure. All right, and again, you'll get very good at this as time goes on. Y'all are just starting out. A little bit of trial and error is going to happen. Again, the most important thing is that you make sure you don't violate any octet rules. All right. The other thing I just want to note, don't be introducing formal charges as well unless you see a charge in that condensed structural formula, right? If there was a positive charge in this formula, then something should have a positive charge. But absent of that, you won't include formal charges. You make sure that everybody's happy, meaning that their formal charge is 0. All right, cool. So now we're going to move on and talk about the next one, which is by far the more important one in this course, the one that we're going to do over and over and over again, what are called bond line structures. So what I'm going to do is I'm going to kind of go to a new page in my notes for some rules. All right, our bond line structures. These, unlike our condensed structures, which are like lines of text, these are drawings as well, but importantly, they're simplified drawings of organic molecules. All right, so like before, I think the easiest thing to do is going to be to show you an example and then kind of pick it apart, and we'll work through that. Okay? So I'm going to go back up to one of the ones that we left room for. This first one here that y'all did on your own. All right, remember we left some room over here. And for right now, you're just going to trust me. If I were to draw the bond line structure of this molecule here, it would be this zigzaggy line right here, these 3 line segments in this zigzag pattern. This is the bond line structure of this molecule. All right, so huge benefit. How long did it just take me to draw that? 2 seconds, right? That's why we love bond line structures. They're also not terribly busy. So if we're representing large molecules, we don't get a bunch of crowded stuff on our paper. We just need to learn how to interpret this thing here. Like, what the heck? How does this zigzaggy line here represent that molecule? Okay? So, importantly, in our bond line structure, the positions of carbons and hydrogens are implied by the drawing. All right? Importantly, how many carbons did I have in my molecule? 4. And so where are those carbons located in my bond line structure? They're at every endpoint and intersection, right? So my carbon atoms are implied in my bond line structure. They're at every endpoint and intersection of that bond line structure, okay? So for our rules here, rule number 1, all right, is the position of carbon atoms are implied at every endpoint and intersection. Oops. Okay. So looking at that zigzaggy line, we know where our carbon atoms are. All right, we also don't have any hydrogens explicitly represented in this structure. So how do I know where the hydrogens are? Okay, again, the position of the hydrogens are also implied, and we fill them in order to complete carbon's octet. Right, so that's all we're going to do after we figure out how many carbons there are. We fill in all the hydrogens just to make sure that those carbons are happy, that they have a complete octet. So over here for this first one, we have 1 carbon-carbon bond. So this first one here needs how many hydrogens? 3. Same with my other endpoint, another CH3. And in the middle here, how many hydrogens on each of those? 2. All right, so in our bond line structure, the carbons and hydrogens are implied in that line structure. The carbons are at all endpoints and intersections. The hydrogens you fill in just to make sure all of your carbons are happy. Okay, so let's just say we said the position of carbon at every endpoint and intersection. All right, our hydrogens that are bonded to carbon are also implied. You're going to add to complete carbon's octet. Make sure carbon's happy with its 4 bonds. Okay. I'm going to leave some room here for one last rule. But before we move on, I'm going to first make sure we know how to read these bond line structures, and then we'll worry about drawing them ourselves. All right? So for these molecules here, let's just zoom in on this first one. I want to know how many carbons there are and how many hydrogens there are, i.e. I'm looking for the molecular formula of this molecule here. All right, make sure we can understand how to read these, how to count carbons and hydrogens. All right, so everybody take a second, copy this down. We'll do this one kind of together, and then I got a few more examples for y'all to do on your own. How many carbons we got? 6, right? Every endpoint and intersection. All right, so C6. The carbons are easy in, again, that they're at every endpoint and intersection. I also just want to point out one of the best double checks that you can do when you're drawing molecules, when we start doing reactions, whatever, is to count carbons, right? So this skill of identifying carbons is going to be really important. It's an easy double check. You'll see me tapping away on my page all the time, double checking that I have the correct number of carbons down. Counting carbons is a great double check here. All right. When we get to hydrogens, we need to fill in. So these ones on the end here need how many hydrogens? 3. Okay. What about this one? Just 2. And what about this one? 1, right? So there are 3 carbon-carbon bonds represented. It does still need 1 extra hydrogen. Okay. So C6H, what is that up to? 14. Okay. Let me just tell you an easy sort of way to make sure that you didn't do anything wrong. Unless there would be like a charge on that molecule, the number of hydrogens will always be an even number for these simple just carbon and hydrogen compounds. All right, so just an easy double check. All right, cool. Yeah, copy down these other ones here. Again, your goal is to give me the chemical formula, molecular formula rather. Whoops. All right, so I'm going to put down a third one here, a third structure. Okay. Again, count your carbons and hydrogens real quick. What do we think these 2 lines next to each other represent? A double bond. And what about the 3 lines next to each other? A triple bond, right? So these are how we represent higher order bonds. Cool. So everybody take a second. Tell me what the molecular formula is for these molecules here. Double check with your neighbor that we're getting the same answer, and then we'll go through them together.
and I'll talk about this here in a second, but we draw triple bonds in that linear way.
All right, remember that higher order bond is going to influence how many hydrogens you need to add in order to complete the octet of those carbons. All right, let's do this first one here.
Scarecrow.
How many carbons do we get? So let's see. So every endpoint, 1, 2, 3, 4, 5. And every intersection, including that middle one right there. Okay. One thing you'll notice is that when we do our bond line structures, we try to keep this like 120-degree angle here between our line segments. But if we have too many bonds, then all of a sudden we have to kind of go to this 90-degree angle sort of thing, right? It gets a little bit more crowded when we have a carbon that has 4 bonds associated with it. All right, I'm going to fill in my hydrogen. So we said C8. I'm going to fill in my hydrogens. All the ones sticking off the end here would have 3. What about this one right here? How many hydrogens? None. It's already got its 4 carbon bonds, or 4 bonds rather. What about this one? Now we need 1. And what about this one? 2. Cool. So if we make everybody happy, we get C8H18. All right. For this one here, how many carbons? 1, 2, 3, 4, 5. All right. How many hydrogens do I need to put on this carbon over here? Right? It's on the end, but it's already got 2 bonds, a carbon-carbon double bond. So it only has room for 2 more hydrogens. And what about this one?
1.
Only 1, right? Carbon double bond on one side, single bond on the other for a total of 3. So these ones here each just need 1 hydrogen to complete their octet. And then when I get to this end over here, now I'm going to need 3. All right, so C5H8. All right, and then the last one. Triple bonds are always a little bit more difficult. What we need to remember is that in order for this to be a carbon-carbon triple bond, there's got to be carbons at either end here. All right, so we actually have 1, 2, 3, 4, 5, 6 carbons represented in this molecule. So I drew my triple bond. Before we go on here, let's just talk about why I drew it like this. I have all 4 of these carbon atoms all in a row here. I didn't do a little zigzag with my triple bond. I made them all in a line. All right, why did I do that? Well, let's think here. What's the hybridization on this carbon here? How many electron regions do we have? 2, right? That triple bond counts as 1. The single bond on the other side counts as 1. So if there are 2 electron regions, what's my hybridization? sp2, which means that its geometry is linear. If I look over here, this one's also sp2, which means that its geometry is linear. right? So when we draw triple bonds, these are necessarily linear. All of these all four of these carbon atoms will sit in a straight line. So that's why we draw our triple bonds, not in the zigzaggy way that we do all of our other ones, but we draw them all in a same line to represent what the geometry of that molecule actually looks like. Cool. All right, let me get rid of this so it doesn't get too crowded. So we got our carbons. Again, we had 6. All right, let's fill in some hydrogens here. These N ones have 3, 2 here, and 2 here. What about these carbons about my triple bond?
No.
They're already happy. They already got their 4 bonds associated with them. So I just need this last one on the end here. All right, so this would be C6H10. All right, so again, these bond line structures, we like them because they're very easy to draw. They're also much simpler to look at than Lewis structures. What we need to be able to do is when we look at these little squiggly lines, we need to be able to fill in with our mind's eye where the carbons and the hydrogens are, right? So again, carbons are at every endpoint and intersection, and the hydrogens you fill in to make sure that everybody's happy. Okay? Again, something that'll take a little bit of practice at first, and then as we go on, it'll become second nature to you. There's one more rule that we're going to add to our bond line structures rules. Okay. And these are for what we call heteroatoms, which in organic chemistry is everything other than carbon and hydrogen. So heteroatoms and their hydrogens must be explicitly represented. Right? They're not implied by that bond line structure. If you have any oxygens or nitrogens or fluorines or chlorines, you will see those chemical symbols in those bond line structures. They're explicitly represented. All right, so again, what we call heteroatoms in organic chemistry, which is everything other than carbon and hydrogen, those heteroatoms and their hydrogens have to be explicitly represented in our bond line structures. All right, so let me show you what I mean by that by going back up to this example that we started out with. I'm going to get rid of my color coding here so it's not too busy. All right, both of these molecules have an oxygen. An oxygen isn't a carbon or a hydrogen, so it would be considered a heteroatom. All right, and so we have to explicitly represent these in our bond line structures. So if I'm going to do this one on the left here, I'm going to need to include 2 carbons. So my line segment here represents those 2 carbons. But now I also have an oxygen with a hydrogen bound. So I have to include that heteroatom, that oxygen, as well as its bound hydrogen explicitly in that structure. Again, bond line structures like Lewis structures, we always need to include our lone pairs. Okay. I drew that oxygen-hydrogen bond explicitly as well because that's how you're going to do it in your homework. I will say that it would not be uncommon at all to just see them run together like this. Okay? In your homework, though, because of the drawing tool, they will make you draw that bond. So I'm just going to include it. Okay? Importantly, again, include the lone pairs. You have to include your lone pairs in your bond line structures. All right, for my next example here, just going back to our Lewis structure, that oxygen actually sat in the middle of those two carbons. So how would I draw that? All right, I'd have a line segment, and then I'd have an oxygen sitting in the middle. Right? So my two carbon atoms are at either end. My oxygen is now breaking up that line segment sitting in the middle here. And what do I need to finish this off? Lone pairs. Okay. So I have my hetero atoms, my oxygens explicitly represented, and like I said, we wrote in our rules, if there is a hydrogen bound to that hetero atom, that also has to be explicitly represented, right? So that O and that H are written in there. In this case here, there were no hydrogens bound to that oxygen, so that's why I don't see any hydrogens in my formula here, okay? But any hetero atom and its hydrogen must be explicitly represented in your formula. Cool? Great. All right. So what we're going to do now is we're going to go back to these four examples that you all drew the Lewis structure for. Now you're going to take these and draw the bond line structure for these four molecules.
can, sort of for the counting purposes, but really our bond line structure wouldn't have that. That's why it's so quick to draw. So for this one here, that one, what I put up there was the bond line structure. So you can count carbon and stuff like that, but this would just have the structure for it. So what we're trying to do is draw those for those.
That requires a carbon and then one branching off like a
Start out. Let's actually do like this one here. So we have 1, 2, 3, 4. So draw me a bond line structure. Oh, I see. This example, I think completely made this up, because this example was one that we did. So this is okay, so let's get rid of this one real quick, just so it's not clear in our notes. So let's do 4 carbons over here, just like we
pretty
had
fun.
here.
I would chapter 7 where it's really fun. But
Cool.
chapter
So
6 is
1,
on
2,
acid, determining which acid was stronger.
Cool. And so this is a good notation for counting carbons. When we draw a bond line structure, we wouldn't always see them. They're implied where they are based on what's already saved. Right? So now if we look on that third carbon, we have 1, 2 extra carbons. So 1, 2, 3. We're going to draw 2 more lines on the yeah, because right here, we go 1, 2, 3. There's this extra one. 1, 2, 3, 4. 1, 2, 3, 4. But on carbon 3, there's another 2 carbons. So that's why we need to draw 2 more lines to represent those 2. Yeah. It really doesn't matter which direction you want to go. Okay, as long as you have 2 more lines on there. Yeah, so there's 1, 2 carbons. You don't want to put them right next to each other. They've got to kind of be pointed in different directions. Otherwise, it's a double bond. Here we go. You would, so how many, where's our, do you have the bond line structure for that one? Let's copy down that, Lewis structure. Let's copy down that Lewis structure first. So you're missing something on there compared to what I have. You need the fluorine, then 2 carbons, then the nitrogen. You only have 1 on there. Yeah. So squeeze 1 on there. Fluorine's on which carbon again? First or
I
second?
knocked out everything that we
Yep.
went over yesterday, and then maybe it took me like 2 hours to finish all of them.
Okay, let's go through these. All right, so for this first one, let me make some room for myself. For this first one, on my main chain, I have these 4, 1, 2, 3, 4 carbons in a row. So that's where I'm going to start, is just drawing 1, 2, 3, 4 carbons. All right, we want to all be able to take a step back and convince ourselves that those 4 carbons that I colored in red here, I've now represented in my bond line structure, right? Endpoints and intersections. But I'm missing something. I'm not done yet. I need to include this carbon up here, as well as its chlorines. So how do I know where I'm going to put that in my structure? I'm going to start counting over. Carbon 1, carbon 2, carbon 3, carbon 4. 1, 2, 3, 4. Where should that orange carbon be? Carbon 3, right? So that means I'm going to add 1 extra carbon here on that 3rd carbon. And it's got a bunch of chlorines attached. Are those chlorines implied in this bond line structure here? Or do I have to draw them in explicitly? I got to draw them in, right? So I'm not done yet. I now have to draw 1, 2, 3 of those chlorine bonds, carbon-chlorine bonds. And of course, because this is a bond line structure, we're going to put in our lone pairs, right? Okay, so for this molecule here, we have its condensed structure, we have its Lewis structure, and we have its bond line structure. Okay, now to be clear, when we were reading our structures before, I went through and I put carbons in here, and I put hydrogens in here, that was just for the purpose of counting, right? We don't want to put all that in there. All of a sudden it makes it more busy and it basically just turns it into a Lewis structure. The point of the bond line structure is that those carbons and hydrogens are implied. So this right here is my bond line structure for that molecule, right? No C's or H's explicitly written. Okay. We're going to go over here, and again, the first thing I'm going to do is pay attention to that main, what we call the main chain, that long set of carbons on there. So I'm going to need 3 of them. So how do I do 3 carbons? 1, 2, 3. All right, again, before we move on, we all want to convince ourselves. 1, 2, 3 carbons. 1, 2, 3 carbons. Right? That's how we do our bond line structure. Those carbons are implied. Now I need to include that oxygen. All right? Which carbon is it going to go on? 1, 2, or 3? On carbon 3. So now I need 1 extra bond to that oxygen sticking off of carbon 3. But it's not a carbon-oxygen single bond. It's a carbon-oxygen double bond. So I'm going to put that second bar parallel on there. All right, and then what am I going to do to finish off this structure? Lone pairs. Cool. All right, so this third one is fairly similar, but now that oxygen's in the middle. So again, I'm going to start off with 1, 2, 3 carbons in a row. I want everybody to take a minute. If you have not already, try to do this one based on what we discussed previously. All right, 1, 2, 3 carbons, 1, 2, 3 carbons. And now I need to put that oxygen, but this time it's on carbon 2. And again, I need to make it a carbon-oxygen double bond with some lone pairs. All right, so getting rid of my markings here, my bond line structure for this molecule is this here. Okay. Does anybody know what this molecule is? We use it a lot, and you're going to use it a crap ton in organic chemistry for cleaning glassware. Acetone. Yep, so that's what this thing is here, acetone. All right, so the last one here, let me make a little bit more room for myself. All right, so this one's a little bit tricky. I have 1, 2, 3 carbons, but they're not all in a row. I have this nitrogen in the middle here. So I'm going to do 1, 2. There's my first 2 carbons. But now I need to draw that bond to my nitrogen, and that nitrogen needs to be explicitly represented. And now I've got my third carbon atom on there. All right, so here, again, just kind of color coding things so we can hopefully see my Lewis structure to my bond line structure. I'm not done. What am I missing? I'm missing a few things. Somebody call one out. The fluorine. All right, I got a fluorine over here on this end. That is not implied in this structure. It has to be explicitly represented. It's off of that very first carbon, so I'm going to draw a bond to a fluorine atom. And I'm going to be good and put in the lone pair on that fluorine. What else am I missing? I need a hydrogen. Where's that hydrogen going to go? On the nitrogen, right? So anything that's bound to one of those heteroatoms, those hydrogens have to be explicitly represented. And then the last thing I'm missing, lone pair. All right, so let me just get rid of my color coding so we can see our final answer here. Here's my bond line structure for this molecule. All right, so In organic chemistry and general chemistry, you learned how to draw molecular structures using these Lewis structures. We kind of simplified our rules for drawing Lewis structures because A, we're going to be restricted to a much smaller number of atoms on our periodic table. We don't have to worry about those expanded octets, but also because we want to be able to draw larger molecules than just those simple ones we learned how to do in Chem 1A. And we also learned how to do these two new structural representations that we use in organic chemistry, our condensed structural formula, and the one that we're just going to use over and over and over again throughout the semester, these bond line structures. All right, so that's what your homework's going to be for this weekend. You're going to be practicing how to read condensed structures and draw bond line structures and review all that stuff about Lewis structures we learned how to do last class period. Cool.